If you really look through your surroundings, at this moment, everything around us appears to be at rest. Or is it? The earth is rotating on its axis, the earth is revolving around the sun, and the sun itself is moving through the galaxy. So, in reality, we are traveling through space at an enormous speed, isn't it? But here is the question: if we are really in motion, why don't we feel it? Why don't objects around us fly backward? To understand these questions and no answer, we must understand a deep and important idea from class 11 physics: why absolute motion cannot be detected. Let us know what do we mean by motion first. In physics, motion is always described with respect to something else. To understand this context, let us see an example. A train passenger sitting inside the train feels at rest, but a person standing on the platform sees the passenger moving. So the same object is at rest for one observer and in motion for another observer. This tells us something important, that motion is relative and there is no special state called absolute rest in everyday mechanics. Now let us see the definition of absolute motion. Absolute motion means motion with respect to a fixed universal reference frame. If this absolute motion is really existing, then we should be able to say that this object is at truly rest and that object is truly moving. But physics shows us something surprising. There is no experiment that can tell us whether a system is at rest or moving with uniform velocity. This idea was first clearly stated by Galileo. According to Galilean principle of relativity, the laws of mechanics are the same in all inertial frame of reference. An inertial frame is a frame that is either at rest or moving with constant velocity. This means if you perform any mechanical experiment inside a smoothly moving train, the results will be exactly the same as if the train were at rest. Let us understand the Galilean principle of relativity using an example. Imagine you are inside a train moving at constant speed on a straight track. When you throw a ball straight up, it comes back to your hand. When you drink water, it behaves normally. And when you walk inside the train, you walk just as usual. Now, if you perform the same experiment when the train is not moving, the results remain exactly the same. The ball still comes back to your hand, the water behaves normally, and your walking is unchanged. Thus, the outcomes of these mechanical experiments are identical in both cases, showing that rest and uniform motion are physically indistinguishable and that all mechanical experiments give the same results in all inertial frame of reference. At this point, you may get a doubt that if motion cannot be detected, then why do we feel motion in a bus? Why do we feel pushed forward or backward if nothing detected at all? And the answer is acceleration. Acceleration is special because it produces observable physical effects. When a bus suddenly starts moving, your body tends to remain at rest due to inertia. So you feel as if you're pushed backward. Similarly, when the bus suddenly stops, your body continues to move forward and you feel pushed forward. These sensations occur without looking outside and can be felt by the observer inside the bus itself. This shows that acceleration can be detected by mechanical effects. In contrast, if the bus moves with constant velocity, no such effects are felt and no internal experiment can reveal the motion. Therefore, uniform motion cannot be detected absolutely, but acceleration can be. Hence, in Newtonian mechanics, absolute motion does not exist, while acceleration has physical meaning and can be measured. This simple idea later became very important in physics. Einstein extended this principle and used it as the foundation of his theory of relativity. But even at the class 11 level, this concept teaches us something powerful. Physics depends on observation and not on absolute states. So finally we can conclude there is no absolute rest and no absolute motion. Only relative motion exists. If a system moves with constant velocity, no internal experiment can detect that motion. I hope this simple idea from class 11 physics changes the way we think about motion itself. Thank you.